Hi guys, in this one I'm going to try and explain a bit about joint distributions. So this is the distribution of more than one type of random variable. And this is often the case. We collect data off more than one person and we'll have a lot of different random variables, and we want to think about the joint distribution. So I'm going to do a little bit about that. Okay, so how do we do that? Let's think of some random variables. So suppose we have n individuals, say. Suppose you've got n people in a classroom and they all have different heights. So we could have a random variable for each person's height. So let's call them y1, y2, y3 up to yn. And so this could be a random variable for the first student in the class for their height, a random variable for the height of the second student, a random variable for the height of the third student, so on, up to n. So we've got an n-dimensional distribution, n variables involved. And we can put those y, if you like, into a vector. Let's call it big Y vector. And that's the vector of all these random variables. So how do we do a distribution on that? So what we can do is we can think about the joint cumulative distribution function, and so that is defined as probability that the first random variable y1 is less than a certain value, little y1, and that's what this comma means, the second variable y2 is less than small y2, and so on up to the last random variable, the last person, if you like, in the class. Their random variable is less than yn. Yeah? So this is what's the chance of the first variable being less than y1, the second variable being less than y2, and the final variable being less than yn. And we can denote that by f capital Y, because it's the distribution of this random vector, y1, y2 up to yn. So that's the joint CDF. Now, what that means in terms of densities, you could write that in terms of a density. It's the integral up to y1 over the first random variable. Integral, let's probably put a dash on that, dy2 dashed y2, so on. It's a multi-dimensional integral, n-dimensional integral, yn, and then it's a joint probability density fy, y1 dashed, y2 dashed, up to yn dashed. So this joint probability here of being less than these values can be written as an integral over up to these values of the density. So you integrate the density up to these values, y1 up to yn. So that's from definitions of the density being sort of the derivative of the full cumulative distribution. So alternatively, you could write fy is basically d to the n, partial derivative, the nth partial derivative, ny1 dy2 up to dyn of fy. So the joint density is the nth derivative of the joint CDF. So that's the basic how you extend distributions to more than one variable, multiple variables, n variables. That's a joint distribution. So now let's look at some special cases. So an assumption statisticians and other people like to make sometimes, it's an easy assumption to make, a nice one to make, is that things are independent. So for instance, I might think that the heights of different students in the class aren't related to each other. You've all come from different families, you're not twins or anything like that. There's no reason why your heights should the height of one student should affect the height of another student. So I can assume probably the heights are independent. So that would mean that probability of y1 less than y1 and y2 less than y2, so on, yn less than ym. The commas here mean and. Is basically can be factored. This is what we mean by independence, that the product of probability of A and B is just the probability of A times the probability of B. So this can be written as probability of y1 is less than y1, probability that y2 is less than y2, up to probability of yn is less than yn. So if it's independent, the joint distribution just factors. And that's very nice when you're doing statistical models. It makes life very easy for lots of things. So we could write that is basically now that's just the cumulative distribution function of the first variable. So we just write y1, cumulative distribution of y1 taken at the value y1. Next one is y2 taken at y2, and so on. F of yn up at yn. Yeah. So, and that is our distribution, joint distribution function. So it's just a product of the distributions of each of them separate. So the what we call the marginal distributions of y1, marginal distribution of y2. So all the margins multiply together and you get the joint distribution. So that's if things are independent. Likewise, it turns out you can do the derivatives here and check this if you like. This is a good little exercise for you to have a go at. But this would also, if that's the case for the joint one, then when you do the derivatives up here, the joint density, the little y there, basically that becomes factored as well. So that becomes f of y1, f of y2, up to f of yn. So both the joint cumulative distribution function and the joint probability density function all factor if the random variables are independent. So that's quite nice. The other assumption that we make, that was one assumption, independent. The other simplifying assumption that people often make, and this is what happened last year in your stats course last year, was that the distributions are identical. So what do we mean by that? We mean that basically f of y1 is f of y2, is f of y3, is f of yn, and they're just some sort of the same distribution, f. So you don't have different distributions for each of the random variables, they all come from the same distribution. They're independent of each other, so it's like independent draws from this distribution, but they're from the same one. And that's what we mean by identical. So in that case then, your joint density would be f of y1, f of y2, and so on, f of yn. Now, when you have both these conditions, independent and identical, statisticians like to call that some variables. They'd say that the variables y are independent and identically distributed. And we have a nice way of writing, instead of writing that all the time, we just write i.d. That means the IID, some variables at IID, means that they're independent of each other and they've come from the same distribution. And that's what you'd get if you sample some random numbers in R from a distribution. It produces a set of independent but identically distributed variables. So that's all great. Problem with that is it's not great for modelling things because, like I said about, say, your heights in the class, I can assume you're probably independent. You're not all twins or from the same family or whatever. So you're probably independent in your heights, but you're not identically distributed. There's certain things that will affect your height. For instance, gender or your sex will affect your height. On average, males can be taller than females. So you're not from the same distribution. There's different distributions going on. So independent is probably okay, but identical is not quite right. And what we can do there is we can think of a new thing. Instead of assuming everything's identically distributed, we can say, let's assume f of yi, the ith individual, that distribution, let's do it for yi, is actually comes from some distribution f, takes for this value yi that we're trying to calculate, and then it's got some parameters here, theta, this distribution is controlled by some parameters that depend on some other variables, xi. Yeah. So these other variables could be something like your gender, your sex, or your I don't know, different aspects that you think might affect your height. Yeah. So these are sort of explanatory variables that affect the distribution, control this distribution. So it comes from the same sort of distribution, f, but this distribution has now got some parameters that can vary depending on x. And this is a more flexible thing than we're assuming still everything's independent, but we're not assuming they're identical. We're assuming there's some x's can control the distributions. And this type of model is called a regression model. And that's what we're going to be doing for most of this module, talking about these sorts of models. So, thank you very much.